The session is on ultracapacitors for electric vehicles. As we all know, ultracapacitors is a new field in which research is going on. Ultracapacitors has got a very good capacity to hold on charge and can be used to good place the batteries. So we have arranged this special session on ultracapacitors. So I now welcome Dr. Varsha Shah to deliver her speech. Over to you, ma'am.
Thank you. So,
I ask the other participants to please keep your mics mute so that unnecessary disturbance is not created.
as dV by dt to be approximately 0, that is a normal mode operation. And the third mode, we call it as a braking or deceleration. So if you look at this, when we say that the dV by dt is equal to 0, that is a normal mode in which the system is operating under steady state condition almost. But when we talk about this accelerating mode and the braking or decelerating mode, they are the transient mode operation of the vehicle. And whenever a system operates in transient conditions, the power requirement will be always different. Power requirement is always different. And depending on the operating mode, that means the rate at which you would like to accelerate it, or rate at which you would like to decelerate it, or rate at which you would like to brake your system, the system demands very huge amount of power or delivered huge amount of power under braking or deceleration condition. So in that case, if I am designing my EV only with battery, then what happens? If you will have only battery, then battery has to supply two things. One is transient power as well as you can say this normal power. It means that the size of your battery will greatly increase. Size of battery will greatly increase, and the utilization, because the system efficiency always depends on the utilization of your source. So if you are not able to utilize your source fully, because the size of battery will be huge, and that amount of power, or that size is only for a short period of time. That is power needed under a short period of time. But for a normal mode operations, the power requirement of your vehicle is very, very small, very, very small compared to the power which it needs during this acceleration mode. It means that whatever the capacity of battery you have, you are not able to utilize fully, which will ultimately reduce the efficiency of your system. It reduces the efficiency of system. So in that case, and we are keeping the maximum amount of the battery power in an ideal mode, we are not utilizing it. And that is always true with any electric motor. And if you need to operate load with the load of, let's say, 5 HP, and the size of your motor is 10 HP or 15 HP, you can imagine that at what efficiency your motor is operating. So here, single source, if we have a single source, the size of battery will be very, very large. It means it will take more space in the vehicle. We have the limitations with the space also, because we have to accommodate everything within our available space of vehicle source. And while oversizing your source, the overall efficiency of your vehicle EV will greatly reduce. So in this particular case, how to solve this problem? Because none of the source available in market will have this capability to provide both the things, that is high energy density as well as high power density. We don't have that facility to have the high energy density source or a high power density source. So in that particular case, we are not able to run our system efficiently, as well as the cost will also increase because the size of your vehicle is again higher. So in all that cases, we need to have a source which will have both the things, high energy density, high power density. But none of the source will have this. So we have to find out some other solutions, and that solution is nothing but the supercapacitor. Supercapacitor have exactly opposite characteristic compared to the battery. Battery has a high energy density and supercapacitor has high power density. And we know that when the system is delivering power at very low rate, slower rate, or for a longer time, we call it as an energy, and the system delivering power at very high in a bulk, then we interpret as a power. So this way, if we will have another storage device along with the battery, then definitely that means we need to have the source which will satisfy this vehicle demand in terms of energy density, because energy density will determine the range of your vehicle and power density will determine your peak speed or the top speed as well as the rate. And to fulfill this requirement, we have the another energy storage device, what are solar or wind power source, because they all are intermittent in nature. So this energy storage device will temporarily support their power balance, or they provide power balance to the grid when the solar or wind power system or wind generators are connected with the grid. It can be also interpreted in terms of microgrid. Even it can operate it in the islanding mode also. Microgrid can be operated in islanding mode or along with our existing grid. So usually microgrid is equipped with this type of solar or wind power generation or any type of non-conventional sources. So where to operate your microgrid independently, again you need to have the energy storage device. So there also, depending on how much power that that your system is required for certain applications, based on that, this supercapacitor will have applications in the field of this microgrid with solar and wind power generation. Even in the wind power generations, it has other numerous applications. That means to adjust the pitch of wings, the supercapacitors are used. Even in the conventional vehicle, the supercapacitors are used. It means that it has a tremendous applications in a different field, even for a small applications like in your mobile phone. In mobile phone also you can use the supercapacitor. You can replace battery, lithium-ion battery, by the supercapacitor. Even for the UPS system. Usually UPS system is again equipped with the backup power. So when the main power gets failure, the UPS system will come in picture, which is usually designed with the battery. Now this has been replaced by battery get replaced by supercapacitor. So it has a tremendous applications, and it provides the different kinds of power. Even it has an independent application also, and people are saying that the supercapacitor may replace the battery with certain, let's say, the material combinations in terms of their electrodes and electrolyte. So with this, let us see the energy storage where it needs. I have mentioned hydro, wind, solar. I have mentioned with the green part. That means these are the green energy, zero emission. The nuclear, natural gas. Again, for a demand response also, you can use energy storage device. For transportation system to maintain the system efficiency and energy efficiency, we use different types of energy storage device. One of them is a supercapacitor. So now, what is supercapacitor? It is also known as ultracapacitor or supercapacitor. It is basically built with the carbon material. The basic material is carbon material. So electric double layer, it is also known as an electric double layer capacitor, also known as a supercapacitor, electrochemical double layer capacitors, or ultracapacitor. The ultracapacitor defect was first noticed in 1957 by General Electric engineers experimenting with the device with the porous carbon electrode. So electrodes are of the carbon material. And supercapacitor was power energy storage cell have been introduced into a marketplace in relatively large volume since 1996 and continue to experience a steady growth. So now the demand for supercapacitor with the different applications are very huge. Although supercapacitor technology has been developed for decades, it has only recently reached a point where it is being implemented more broadly in a number of industries, or at different places. So this supercapacitor is specially designed capacitor capable of storing enormous amount of electrical charge. It can store a very high amount of electric charge. Structurally, we can say that, as you all know about the normal capacitor, what we have plate, and in between we have dielectrics, right? And then this will act like a capacitor. So it is almost similar to this, but this plate will be interpreted in terms of electrodes, positive electrode and negative electrode. Then the separator as a membrane separator, and instead of usually dielectrics, they have the electrolyte. So it consists of two electrodes, membrane separators, and electrolyte. You can, if you want to see this, it is looking like this. This is what we call it as, this part is nothing but your porous electrode. This is positive. This is negative porous electrodes, and in between whatever you have is gray color. That is nothing but electrolyte. And on other two sides you have the current conductors, and in between you will have a membrane type separator. Energy, C is the capacitance value of C, V is the voltage across the electrode, between these two electrodes, how much voltage we are applying, that is that voltage. Q is charge, and epsilon naught, epsilon is a permittivity of the electric material. And so the supercapacitor uses electrodes having a high specific surface area and thinner dielectrics. And as you know that the capacitance value increases if the area of the electrode will be very, very large and the distance will be very small. So, and that is, it has a high specific surface area compared to the normal capacitor value of capacitance, and that capacitance value is in terms of Faraday, not in terms of microfarad. The conventional capacitors will have the rating in terms of microfarad, but with a very, while this will be expressed, this has the capacitance value in terms of Faraday, but the voltage level will be very small, 2.7 volt to they have reached to the 5 volt. Still in market, 5 volt supercapacitors are still not available. Yeah, some prototypes are available in market. So depending on the define, and this capacitance value in terms of Faraday will start from, I can say, 0.1 Faraday to 3000 Faraday to 50,000 Faraday. So it has a tremendous high value of capacitance, and that is because of high specific area and thinner dielectric. Supercapacitor uses electrodes having high specific surface area created by typically porous carbon. We are using porous carbon electrodes with small charge separation. That is, the charge separation is in terms of angstrom, 10 angstrom. The performance of supercapacitor rely on factors such as electrochemical properties of the electrode material used, electrolyte, and the voltage range. This voltage range or voltage window will be again defined by what type of electrolyte that you are using. And the capacitance value will be defined by this electrode material, what type of electrode material you have. Accordingly, you will have the different value of capacitance. But the voltage range will be defined by this electrolyte. So in case of supercapacitor, two electrodes are insulated by the membranes impregnated to the electrolyte. And membrane separator only permits the ion mobility but prevent electric oxides, manganese oxides. Conducting polymers are polyaniline, and in case of nanocomposite based material, on which now people are focusing their research, and I will show you one of the can say the company, startup company,
have designed the supercapacitor, graphene-based supercapacitor battery using this nano-composite-based material with the help of graphene. So carbon-carbon composite, carbon and metal oxide composite, and carbon and conducting polymer composite. It means that it is, you can say, the combinations of carbon materials and the pseudo-capacitor material. And particularly the carbon materials have successfully utilized in the commercially available supercapacitor because of their advantage, such as the cost for the carbon material is low, high specific area, availability, good conductivity, high electrochemical stability, and wide operating temperature window. The porosity parameters, including pore size and pore size distribution, equally exerts an important influence of practical SC capacitance because these parameters can have a major impact on active electrode surface possible for accessible to the electrolyte. So this, as I already told you about this, that porosity and the pore size and the accessibility to the electrolyte ions will play an important role to determine the capacitance value of the supercapacitor. The capacitance culminates when electrodes have the pore size close to the ion size. This ion size means electrolyte ion size. If it is very close to this, then the energy storage capability of the supercapacitor increases, or the capacitance offered by the supercapacitor increases. The only limitation with the supercapacitor is the low breakdown voltage with which it is working, that is 2.7. People are now claiming that it can go up to 5 volt. So if we look at the electrode activated carbon, so this is either activated carbon powder, mixing, charcoal, solvent, etc., carbon bonded on metal foil. So this way, this activated carbon material, different types of carbon materials with the different way, they will be, they are used to form an electrode. This is a microfine carbon powder, consists of 3 types of particle size: microporous, metaporous, and macroporous. So in every, hello? Pore size is important for electrolyte content. This is the most important things, which then only it has a more value of storage. A mixture of the 3 size used for the best result. And the carbon source may be a coconut shell, hardwood sawdust, petroleum coke, and coal and pit. And they will have the surface area range varying between these. Then electrode materials, that is a carbon nanotubes. They will have like a nanotube structure and high cube density, that is 10⁻12 to 10⁻13 cm per cm square. Tube length is 100 to 300 micrometer. Energy density is greater than 60 watt-hour per kg. Comparable density to nickel molybdenum hydride battery. And power density is greater than 100 kilowatt per kg, 3 times higher than battery, and the life cycle will be 3 lakh cycles. Then the graphene materials, it has again opened up a new way to design this supercapacitor as like a battery. So lasers scrub graphene power 20 volt per cc, comparable to lithium-ion battery. Surface area is 1520 square meter per gram, and it can go up to 2600 square meter per gram. Binder-free active layer will be there, no binder is required, and energy density up to 85.6 watt-hour per kg. They have reached up to this. Other is a aerogel material. Aerogel will have a 1.9 mg per cc, and 90 to 95.5% is air, yet can hold up to 8,000 times their weight. And surface area up to 3,000 square meter per gram, and energy up to 90 watt-hour per kg, that is 70% of lithium-ion battery. And it has a very good, excellent thermal insulation. This is the most important part for the energy storage device, that they must provide excellent thermal stability. Electrolyte will also play an important role to determine the voltage window for the supercapacitor. It may be of three different categories: liquid electrolyte, solid state, or the quasi-solid state electrolyte, and redox active electrolytes. So aqueous electrolytes are acid base, alkaline base, and neutral base, that is Kc. And non-aqueous electrolyte is organic electrolyte from the Teflon, that is ionic liquid and mixer of that. And in case of solid state, dry solid polymer electrolyte, gel polymer electrolyte, and inorganic electrolytes. And redox active electrolyte is aqueous electrolyte, organic electrolytes, ionic liquids, and gel. It has a different types of electrolytes. But these electrolytes is another important component that affects the SC performance. The general requirement for the electrolyte encompass large voltage window, high ionic concentration, high electrochemical stability, low resistivity, low viscosity, low volatility, and low cost, because they will determine the voltage window as so. Aqueous electrolyte, organic electrolyte, and ionic electrolytes are mainly used. Generally, the supercapacitor with the aqueous electrolytes exhibit better performance in terms of the capacitance and power delivery, since the aqueous electrolyte can have the higher ionic concentration and low resulting resistance. But the voltage window will be very low of 1.2 volt. And we know that is the reason why the SC stored energy capacity will reduce, because the voltage is low. But in contrast, the organic electrolytes can offer a voltage window as high as 3.5 volt, making it more preferable in SC manufacturing. And liquid ionic liquid refers to the smelt salt at certain temperature, which possesses several desirable properties, including low vapor pressure, large voltage window, high electrochemical stability, and so forth. It means that many times it can be added with the salt. I will show you in the next slide. Because they are the key parameters, which depends on its energy density and power density, as I have already told you. So energy density is responsible for voltage window and ion concentration of electrolyte in supercapacitor, and power density is mainly affected by the resistance of electrolyte. So organic UCs have higher energy density and terminal voltage than the aqueous UCs. Organic UCs are typically used for powering EV. For enhancement in the ionic conductivity, different salts are mixed with both organic and aqueous electrolytes. This is also increases the range of temperature of electrolyte. It means that it will provide more thermal stability. Then the ionic concentration will also increase with this. And as the ionic concentration increases, the energy density the power density will increase, and the energy density is again related with the voltage windows. Thus, this type of salts are required to be added in limited amount for prevention of ionic depletions at high voltage. Again, supercapacitors are in a symmetrical or asymmetrical configuration, such that they either have the electrodes of identical material or not. If they are built with identical materials, they are symmetrical in nature, or they are unsymmetrical in nature. Lead carbon capacitors are a good example of asymmetrical supercapacitor. Usually, it is very difficult to have the symmetrical identical material. Carbon nanotube UC technology have a high power density. It can go up to 100 kilowatt per kg, and energy density of 60 watt per kg. Pseudo-capacitors and hybrid capacitor exhibit good performance in energy storage applications because of their high power and energy density. Now, recently the lithium-ion capacitor has been developed, which have a higher terminal voltage and higher energy density than the other supercapacitor. And they have claimed that it is 80 watt-hour per kg. I will show you some other slides in which it can go up to 86 watts per watt-hour per kg. So this is known as a hybrid, in which one electrode is a battery electrode, and second electrode is a supercapacitor electrode. So you are getting one characteristic with related to the supercapacitor, the high power density, and battery electrode with high energy density. And they can be coated with the other material to improve its functionality. We'll see that in the next slide. This is like a supercapacitor for the different applications, and you can see their temperature range and their other operating parameters. The energy density you can see here, the charge cycle you can see, the voltage level, and their life cycles. The most important thing that is a cell balancing circuit, as the supercapacitor voltage is cell voltage is 2.7. To have, let's say, 16 volt supercapacitor, you need to have the 6 supercapacitors to be connected in series to get you will get a 16.2 volt. It means that we have to connect 6 supercapacitors in series. So cells are connected in series as well as parallel to improve its current capability to get a desired voltage and capacitance and current. So usually how to, let's say we are connecting the number of capacitors in series. But as we know that the electrode characteristic may not be same for all the capacitors, and that's why they will have the different voltage range. Some capacitor may get charged and some may not get charged. You see connected in series, but how to connect UC in series, and then after you have to connect that series connected UC with the cell balancing circuit. So before we directly connect this supercapacitor to a cell balancing circuit, we have to go through the certain criteria, and based on that only we have to make a string of UC connected in series, and then after that will be connected to the cell balancing circuit. Unfortunately, supercapacitor may have a tolerant difference in the capacitance, resistance, and the leakage current. They have the different tolerance. And this difference creates an imbalance in the cell voltage of supercapacitor wired in series when we charge it. So it is important to keep the voltage on any single cell below its maximum recommended working voltage. We don't want to go above that. Otherwise, supercapacitor could degrade from electrolyte decomposition, gas generations, or effective series, or increasing the effective series resistance. It will increase the effective series resistance. So that's why what we need to do is we have to go with the procedure which I am telling you. The factor that initially dominates imbalance in the capacitance, in a capacitance difference between the cell. A cell with a low capacitance will charge to a higher voltage in series string. That means the capacitors which have lower capacitance value will charge fast than the capacitors having a higher capacitance value. And usually the supercapacitance value may get differ as much as by 20%, plus or minus 20% from cell to cell. So for example, in the batch of supercapacitors, suppose we'll have, it is possible to find one cell rated at 2.7 volt and the capacitance value of 100 Faraday, and next to the one is 127 Faraday. One is 100 Faraday, other one is 127 Faraday. Their voltages, let's say, are same. We would like to charge the same voltage. So if these two cells are wired together in 5-volt pack, one could settle at 2.2 volt and the second could settle at 2.8 volt. Having a larger value will get charged at 2.2 volt and the lower value of capacitance will get charged at higher voltage, which is out of specification. So in that case, these are the 4 steps that will ensure cells in series stack will balance. Determine the individual capacitance value of each cell. Group the supercapacitor with a similar capacitance value. To realize voltage level that are within limits to each cell in the stack, the capacitance value of each cell must be reasonably close to that of the other cell. That is the first thing, that we have to group them into an equal value of capacitance. And once the cells are grouped by the capacitance value, determine the leakage current of each group. Finally, the group together cells that have the similar capacitance and leakage current. So we have to make a group of those capacitance having a similar capacitance value and the leakage current, and separate voltage balancing circuit for each group. Then we have to connect a separate voltage balancing circuit for each group, and that way we can do the balancing of this supercapacitor. And this is what has been shown here. If you can see here, one voltage balancing circuit will be there. This is another voltage balancing circuit. This is third voltage balancing circuit. And of course, this voltage balancing circuit is very simple and very cost effective. How to measure capacitance? And for that, usually we do a test like we can charge the supercapacitor from its 0 value to its full rated voltage, which has been mentioned over here, that is a 2.7. Keep it on a rest for 30 minutes. And when we keep it for a rest in 30 minutes, you can see that its terminal voltage, which has reached to 2.7 volt, has reduced by certain amount. And that voltage drop is nothing but the redistribution of charge in the supercapacitor. Because this supercapacitor is like I have already shown you in form of layers and a long sheet. So when I'm applying the initial part of your sheet will be connected with some source to charge your supercapacitor, then definitely the near to this terminal part will charge to a full level and it will immediately show that okay, the capacitor get fully charged. But for probability maybe that the internal part of your supercapacitor may not get fully charged. And that's why you have to keep it for a 30-minute rest so that the complete supercapacitor get fully charged. And when it gets fully charged, the voltage reduction will appear. This will indicate that the charge redistributions will take place. And that's why now the supercapacitor terminal voltage reached to this value. And this is usually defined as the voltage drop in the supercapacitor. And then you can discharge it. So this voltage is 80 volt, 80% volt, and this is a 40% volt. So it is half the voltage. From this value to its half the voltage value. As I have told you that this will exert a 75% of the energy available in the supercapacitor. And now using this very simple formula, the C is equal to Y into T2 minus T1 upon dV, where T2 and T1 are nothing but the voltage level, that is 2.16 volt to 1.08 volt. Or even you can start from here also and you can end up with this. And you can, and we are discharging these with a constant current. So this way you can calculate your capacitance. The same can be mentioned here. And for example, let's say if you take a 185 seconds, because you have to measure the time also, measure this time difference. To charge, you see, from 8 volt to 12 volt. And let's say we have the charging current of 9 ampere. The capacitance will be calculated as how much time it is taking, T into the current divided by V final minus the initial. Initial voltage is 8 volt and it's charged to 12 volt. So this will determine the capacitance value. This is a very simple method, approximate method by which we are measuring the capacitance, but to have the accurate measurement of capacitance and the resistance, this is impedance spectroscopy, constant current charge method, and the cyclic volumetric method is used to determine the capacitance value. The ESR variation is basically temperature dependent, but there is as such no, can say the standard has been yet established for ESR with respect to their temperature variation. So we may assume that the ESR may be constant for the range of operations, or if it vary with respect to temperature, then you can test your supercapacitor at different temperature and measure their resistance. And this is again, I can say the same characteristic which I have shown you, but this most important part is here and here. This is the pulse width for which we are discharging the supercapacitor, and based on that we find the energy extracted from the supercapacitor. You can calculate the power density and energy density using this half C V square divided by weight and V square by 4 into ESR into weight. That is the power density, and for the different capacitance value, you can get a different power density, energy density. You can see the energy density is low, but power density is very, very high. And you can look at this. This is the instantaneous current, that is a maximum current that this BCAP, that is you can say the capacitor with the 650 Faraday. This is 1200 Faraday, 1500 Faraday, 2000 Faraday, and this is 3000 Faraday. And their weight has been mentioned, and their current for 650 it is 680 current, 930, 150 to 1900 ampere when you go with 3000 Faraday. Of course, this is the, you can say, the instantaneous current, maximum current that can be supplied by this. But it can supply, you can say this 3000 Faraday capacitor can supply around about 100 ampere current or 150 ampere current, depending on the how, means if you are having a 3000 Faraday and if you have the this 15,000 Faraday, depending on what type of Faraday and how you are connecting them, how many number of this are connected in series and parallel accordingly. But the individual, you can say that the 3000 Faraday will provide 100 ampere continuous current in terms of, you can go up to 1 minute. Usually this is with the 10 second to 20 second. And we know that this time duration is always matching with the acceleration of your vehicle. So we are accelerating our vehicle from its 0 speed to the rated speed within the maximum time of 20 seconds. That's why it has a very good application. That means supercapacitor can perform, means provide very good acceleration power. These are the way by which you can combine these two power, energy storage, power delivery component, and the primary energy storage as a battery, this as a supercapacitor, and then this provides a peak power demand and continuous power. Power demands, you can use this. Again, for these also you can have the two-way operation. And in this particular case, when we are using supercapacitor with battery, the peak power will be managed by the supercapacitor, and battery can be, now the size of the battery will greatly reduce, and this will again says that the overall weight space requirement will further reduce, and we are able to utilize the full capacity of battery. And that's why we are operating this device at its maximum efficiency. And low ESR of ultracapacitors will improve the efficiency in recapturing of energy and overall system performance. But as I have told you, that the supercapacitor voltage will vary with respect to when it get discharged, right? And if I'm having, let's say this is my supercapacitor, I'm connecting with some load. Usually we know that the load is always operating with the constant voltage. When we try to deliver power from supercapacitor to this load, if suppose this supercapacitor is of 16 volt, and let's say load is demanding of 12 volt, up to 12 volt it can deliver power to the this load, but as it start reducing below 12 volt, then we are not able to maintain this voltage constant, and in that case we are not able to provide power to this load with the required voltage level. So usually the supercapacitor is always provided with the power converters. What they do is this output over time curve that is decreasing with respect to the power demand. Output over a time through this power converter you can maintain constant. This voltage level you can make constant. So this power converter output is steady deposit despite drop in the supercapacitor voltage on usages. This is the voltage drop in the usages of the supercapacitor, but at the load point, your output voltage will maintain constant with the help of power converter. And that is the reason why the power electronics play a very important role whenever you want to use supercapacitor as an energy storage device for any application. Then only you are able to utilize full capacity of supercapacitor. This provides a precise or better than the battery output voltage right until the supercapacitor is fully discharged. Of course, you have to design your converter in such a way that if my supercapacitor is of 16 volt and then it can work up to 8 volt. And let's say here it is demanding 16 volt, load is demanding 16 volt. Then this power converter should operate in such a way that when the supercapacitor voltage reaches to 8 volt, still this power converter will maintain this output voltage to 16 volt. So that way we have to design this power converter, and this power converter is bidirectional. At the time of delivering means power, it operates in one direction, in this direction, and at the time of capturing the energy, it works in this direction. So it is a bidirectional DC to DC converter. This is nothing but DC to DC converter because the supercapacitor voltage is a DC voltage. And what we need is a DC bus voltage. I think applications I have already told you, again I'm just repeating: grid stability, peak load and surge management, UPS, which I have already told you, battery backup, hybrid electric vehicles, solar and wind energy storage, standby and backup also for right through supply. Even the supercapacitor. Even the supercapacitor can be used for the drive application. In case of power failure, condition, failure conditions, momentarily, the supercapacitor will support the functionality of drive, because we all know that electric drives are very sensitive to any abnormality occurring in the system, even for a short period of time. So that short period time will be supported by this through the supercapacitor, and we can maintain the continuous operation of this drive even under the failure of power supply. And by that time, the backup power system will, the power supply will come in picture, and the capacitor will get disconnected. So it provides, for a drive application also, we can use supercapacitor, especially under this power failure conditions. In case of EV, mainly regenerative braking, releasing power in acceleration, starting power in start-stop arrangement. I think in my previous class, I have told you about mild mild and micro hybrid, where usually we use this energy storage device for start-stop operations. So usually you can use it for the start-stop operations. It can regulate voltage to the energy grid. This is the most important applications of EV energy storage device. Let's say this is your grid, and through this grid your battery, or you can say your EV, has been connected, right? It may have a supercapacitor based EV or supercapacitor plus battery based EV. Then this EV has been connected with your grid. Usually in the normal case, there is always power flow from grid to EV for charging this. But under other circumstances, when your grid is operating in the peak power mode, peak demand mode, in that case, this EV can provide real-time power support and reactive power support. So it can provide this, and that's why the regulated voltage to the grid, energy grid, that means it supports reactive power. And if some additional power is demanded by the grid, then it can supply the real time. But of course, for the real time power supply, supplying power to the grid, it depends on the, or can say the consumer willingness, because ultimately it is related with the charge. Lowering loads and assisting when the loads are lifted. So in case of lift also, you can use supercapacitor. I will show you one more example in which city bus is driven by supercapacitor only, no battery. I think I've already discussed. And usually you can see these are the different modules provided by the different manufacturers, 16 volt, 56 Faraday. So how this, because all capacitance, when they are connected in series, their equivalent capacitance will be always calculated as if they are connected in parallel. So 16 volt, 500 Faraday, basically this unit is nothing but the 3000 Faraday units are connected in series. And when they are connected in series, you have to divide by 6, so it offers 500 Faraday. So depending on what is a single unit capacitance value, and based on that, you can have, their voltage ratings are always 2.7 volt. But the capacitance value will vary depending on what type of that is the supercapacitor cell that you are selecting. They may be used for you can say 2.5 megawatt turbine in Clipper, 2.5 megawatt turbine, and G 1.5 megawatt turbine. Also, this type of supercapacitors are used. So turbine manufacturers and operators rely on ultracapacitor energy storage as a preferred choice for pitch control backup power. So it has a tremendous applications. Different types of applications are there where you can use. This is again a combination of lead acid battery with the supercapacitor to get an ultra battery, I can say, and which will this will provide. You can see the size also. The battery size will be much larger than the supercapacitor size. So weight, tremendous reduction in the weight when you use when you have the supercapacitor. This is different types of hybrid batteries in which you will have the two combinations. Now this is a new graphene supercapacitor battery, in which, as I have told you, that in pursuing higher energy density with no scarcity of power density, that means we want to have both power density and energy density to be very high. A supercapacitor battery hybrid energy storage device combining an electrochemical double layer capacitance type positive electrode and lithium ion battery type negative electrode. That means that two separate electrodes are used. One is corresponding to the lithium ion battery, one is corresponding to the electrochemical double layer capacitance, and then the graphene is introduced to both the electrodes. That is Fe3O4, which is nothing but your the material for the lithium ion battery, and that has been used with the graphene, that is a nanocomposite with the high specific capacity as a negative electrode material, and a graphene based three-dimensional porous carbon material 3DG graphene with a high surface area approximately 3355 meters square per gram as positive electrode material. And what they have observed that if you want to have the energy density of, it offers energy density of 147 watt-hour per kg with the power density of 150 watt per kg, then that is a reduction, that is an equivalency between energy density and power density. But this will also offer 86 watt-hour per kg even at high power density of 2587 watt per kg. And it has been detected that so far the highest value of the reported hybrid supercapacitor. And still people, this is a very, the research area in which people are working. Of course, maybe the chemical branch or the chemistry people may focus on that. Furthermore, the energy density of hybrid supercapacitor is comparable to a lithium-ion battery, and the power density also reaches that of the symmetrical supercapacitor. It means that we are able to get both the things, indicating that the hybrid supercapacitor could be a very promising novel energy storage system for fast and energy efficient storage in the future. Of course, I can give you an example of Indian youngsters made a graphene supercapacitor battery for electric vehicle. They have used the same technology and they have made that, and they have built a two-wheeler, and in this two-wheeler it is 1 kWh. 1 kWh battery they have made, which is a combination of graphene supercapacitor battery, that is a supercapacitor terminal, battery terminal, and that will be provided with the graphene material. And the critical factors required for battery can be now managed by this combination, that is a high specific power, safety, low self-discharge, wide operating range. As here they are using a different composite of they're using a different composite of the graphene. They're using a different composite of graphene, which will provide even a lower discharge. That means usually the supercapacitor will have high self-discharge, but the composite material will provide offer can say the features with low self-discharge, safety, wide operating range, affordable cost, long shelf life, non-toxic, long life, and fast charge capability. This is the most important things, and what they are claiming is from 0% to 100% charging is possible, and 100% to 0% discharging is possible, and which you can achieve within a 15 minutes of time. Maximum within a 15 minutes of time you can achieve this. This is what they are claiming. High specific energy, high specific power, also they have got it, and they can charge from 0% to 100%, and they can discharge from 100% to 0%. And what they these two are the current collector. This is anode and cathode. As cathode will be from the battery material, anode is from the supercapacitor material, and in between you will have the electrolyte. And this electrical current reaches the cell by conductive surface at both ends of the stack, because they are can say this is double layer current, or sorry, the double layer electrode as anode and battery as a cathode. And the way the current is in, it can get charge, and current is out, that means it can discharge. So this is one of the applications with the Gigadyne. Gigadyne is the name of the startup company, and they have built a hybrid supercapacitor technology in which they have already implemented it. And what they are claiming is that they will appear within 2021 with the full market. And what they says that we are able to save 3,000 billions of dollar by 2030. That is what they are claiming, because now we are manufacturing in India. That's what they want to say. Other application is 450 volt, 28 Faraday, 910, whatever ultra-capacitor pack that has been used for the bus. And I have seen that bus which is running in China, Beijing. And what they, at every stoppage, which may be of maybe a minimum of 1 kilometer. So up to 1 kilometer, the supercapacitor will provide power to the bus. And when it reaches to the stoppage, it can immediately charge within the duration by which the passenger will get down and get in. Again, it gets charged, and it will again provide the next, you can say the next road traveling for, means it provides power for the next travel range. So that way continuously it can get charged, discharged, and it will operate this bus. And this is the figure of this capacitor bus, AC 41-seater in China. And it has 2.25 kWh ALDC, 60 kWh battery, and 45 miles within AC. And charging time is 32 to 40 second ALDC and 6 hours per battery. And if it is not provided with the battery only supercapacitor, then 5.6 kWh ALDC, 3.5 miles with AC, and charge time is only 6 minutes. And this is with the battery, if it is provided with this. Now, as I have told you that the supercapacitor will have different characteristic, battery will have different characteristic, and if we will combine these two storage devices together to define the need of power and the energy need of a vehicle. And that's why we need for hybrid power source. So designing a single power supply source to meet a peak load demand leads to an uneconomical and inefficient design. So better approach is to have the different source for a different section of load demand, because we have the load demand profile is different, accelerating, constant speed, and deceleration. So battery is a high energy density energy storage device which is better suited to meet the average load demand, and supercapacitor for the high power demand. So this battery plus UC will be a super device for EV application. And this will reduce the battery size and lead to a better efficiency and cost reduction. So if you want to design this hybrid source, then the first step is identification of the hybrid source, battery, supercapacitor, then what type of supercapacitor that you would like to select, what type of battery chemistry that you would like to select. After that only you have to do the modeling of this battery and the supercapacitor, and then you have to develop an energy management algorithm which may be based on rule-based And that way you can have the sharing of power between the two sources. The sharing of power will be managed by this energy management system. Then you have to identify the HESS topology. Topology means whether all battery and supercapacitors are not using any power electronics device, or one device is using power electronics device, other is not using, so passive, semi-active. Active means both battery and supercapacitors are controlled through power electronics device. Then you have to identification of DC converter and inverter, what type of DC converter that you would like to use. So identification of DC to DC converter and identification of DC to AC converter, that is related with the motor applications. And then whether it is a what type of switch is semiconducting switch, you have to select the appropriate semiconducting switch, and you have to select the appropriate semiconducting material for that particular switch. Because now now for vehicle applications, people are focusing on not on silicon based power electronics device, but they go with the silicon carbide and gallium nitride based power electronics device. That's because they have a good temperature withstand capacity, as well as the reverse recovery part is concerned. These two are more efficient than this silicon based power electronics device. So you have to find out a different topology for DC to DC converters, and whether they are unidirectional, bidirections, and again then you have to convert this, you have to control that DC to DC converter so that appropriately you can have the control current from both the source. And again, the implementation of electrical vehicle characteristic, that is a dynamical vehicle behavior that we must know, and the regenerative braking part also we have to consider. So this way, this is an overall design, complete design of, I can say, vehicle with the hybrid energy storage system. So this hybridization of energy source may be only passive. I will show you with an example. Semi-active, UC battery. Hello? Hello? You may have the semi-active configuration in which either battery or UC will only have one DC to DC converter. Fully active means both are connected with the DC to DC converter. So this is a parallel connection. In battery, supercapacitors are connected in parallel. Now you can visualize that if suppose both are working with the same voltage level, then the capacitor, as the capacitor will have the low resistance, it starts supplying power to the load. But as soon as the voltage of supercapacitor becomes a terminal voltage of battery, supercapacitor cannot deliver power to this system. The reason is that these two are connected in parallel, and that's why the supercapacitor voltage will float with the voltage of battery. And what happens is the battery will supply power to the system as well as it will charge this. So that's why it has a disadvantage that the supercapacitor terminal voltage continuously varies with respect to load variation and voltage variation at DC link. So UC energy is ineffectively used. We are not able to use the complete energy available in UC. So this is one of the simulation that has been shown with that equivalent representation of battery with the battery voltage and the resistance and supercapacitor capacitance value and their RES. And I have taken this example with the battery voltage is 16 volt, ultracapacitor voltage is again 16 volt, and they can be charged with the pulse load of a different duty cycle. So you can see here, this is the pulse load, this is the, you can say, high power, and this is the low power in which your current distributions will take place. You can see here initially the supercapacitor is supplying power, and then after the battery will come in picture and battery will supply power during this period. And it may provide power to the supercapacitor also. So supercapacitor get charged through battery, because this is the, as we know that the battery terminal voltage won't get reduced as it's supplying power to the load. You can, this is in a very larger form. So this is nothing but the green is supercapacitor power and this is the battery power. And here the capacitor gets charged to battery. So we will have the limitations of the passive hybrid that UC voltage and load voltage both float with the battery terminal voltage. This does not allow the utilization of full power capacity of supercapacitor, and that's why we cannot select upper limit of UC voltage randomly. So in that case, we may go with the hybrid energy storage system for vehicular applications in which this is a supercapacitor. We have the different topologies. This is a semi-active topology in which supercapacitor is connected with bidirectional converter, and then after the battery, this all three are connected in parallel. So DC to DC converter will maintain the same voltage as the battery voltage, and then after the power will be supplied to the motor. So in that case, we have to select which device will supply power, supercapacitor or battery. Here the advantage is that only one bidirectional converter is required, but the disadvantage is that because we are using it for supercapacitor, and as the supercapacitor terminal voltage reduces, to maintain that current, the current rating of this bidirectional DC to DC converter will increase, because we know that when voltage decreases, current has to increase to maintain the same V into I product. So this bidirectional DC to DC converter must be of a high current rating when the supercapacitor voltage reduces from its rated voltage. That disadvantage, but it provides a very good control for this supercapacitor. Then you will have another topology in which battery, bidirectional converter and supercapacitor. So here the disadvantage is that the variation of DC link voltage due to supercapacitor will be there. So you have to design your inverter, or you have to control your inverter in such a way that whatever variation that has been supported by this supercapacitor at DC link must be managed by this inverter control algorithm. But advantage is that the low rating of DC to DC converter is required. And multiple converter configurations both will be provided with separate DC to DC converter. Advantage is that you can control both the source, and you can have the different rating of different voltage rating and power rating of the battery and supercapacitor. And here highly varying UC voltage can be fully utilized. But two different. Hello? Hello? Please switch off your mic. Hello? Disadvantage is that the two full size converter is used. Converter adds weight, cost and size and complex control. And this is a multiple converter configurations within one single unit, and battery and supercapacitor can be connected like this. This will overall reduce the cost of the two full size bidirectional converter that is used. Example with the active hybrid. This is the battery has been directly connected, while supercapacitor is connected through this DC to DC converter, and these two switch will operate in two different mode, boost and buck mode. So usually the supercapacitor voltage to match with the DC voltage, we have to operate it in boost converter mode, and at that time the supercapacitor is supplying power to the load. And whenever this load may be again a bidirectional load, that means it can sink and source the current. So that time this switch will come in picture and it will operate and run the additional charge into the supercapacitor. And this battery will, this switch will be only in the on and off mode, while this is in the chopping mode. This switch is in chopping mode, we have to chop it as per our requirement, and either we can have the power transfer from supercapacitor to load or load to supercapacitor. And battery will provide power only in one direction whenever the load is demanding power, maybe along with supercapacitor or individually. And this is the distribution of current. You can see that very high current from the supercapacitor side. This is your load current, and this green one is your battery current. So battery is not supplying any current during this period. Battery is supplying for the normal requirement. So we can say that the advantage will be definitely offered by the converter. So adding DC to DC converter between battery supercapacitor yields several advantages. Supercapacitor voltage can be different from the battery voltage, which offers flexibility with respect to design of battery and supercapacitor array. Power capacity can be much higher than that of the passive hybrid without exceeding the safety limit of the battery current. Of course, here the most important part is that we have to control the battery current, otherwise it will degrade the battery functionality. So load terminal voltage can be kept almost constant with respect to the vehicle driving conditions. So these are the advantage what we are getting with putting a DC to DC converter in this energy storage device to build or to design a hybrid power source for EV. Again, it will regulate the power flow from input to output. The weight of the power source for given peak power can be smaller than that of the passive power source for the same load. This is another advantage what we are getting. And DC to DC converter can also serve as a battery charging regulator, while a passive hybrid source would require a separate battery charger. So if you have, then the same can be used to charge the battery. This partially removes the limitation of adding series cells of UC to an upper limit set by the maximum allowable ESR. So it will allow you to use more number of UC cells in series. So this is one of the example. Other example, that is a supercapacitor is used to drive the electrical vehicle motor, or you can say the let's say this is the induction motor which is connected with some load, and this is supercapacitor, and this is bidirectional converter, which is you can say the DC link, and then you will have the three-phase inverter. This is DC to AC converter that will provide power to AC, that is two. So both are, this is a bidirectional, this is also bidirectional. So power flow during deceleration and braking operation of the vehicle in this direction, and power flow during acceleration and constant speed operation of the vehicle in this direction. So while designing this, and when you want to do the simulation, what should be the load? How to consider that load? This is the most important part. How to consider this load? And for that, we need to have some information about the vehicle itself. This is basically the internal diagram, and this capacitor bank is used to operate this induction motor as a generator under regenerative mode operation. So the reactive power, during that time, the reactive power will be supplied through this capacitor bank. And remaining thing is, this is nothing but a DC to DC converter. You can choose your topology, whatever topology you want to select. And this is nothing but your DC to DC converter, DC to, this is nothing but your DC to AC converter. And this is again the most important part. This capacitor, DC link capacitor, has to be designed appropriately so that the ripple can be minimized when the power will be supplied to the induction motor. To simulate it, the input data will be always in form of the driver is driving a car. So have the two pedals, accelerating pedal and brake pedal, or the decelerating pedal, whatever it may be. You can increase your acceleration, and the same accelerating pedal you can decrease it, and this is, you can use it for the brake. And based on that, when we drive a vehicle, we can get this driving profile, that is a speed versus time. So these are the different driving profile. This driving profile is referred to the New European driving cycles. Basically, it is used for testing purpose, testing a new built vehicle. And this is UDDC, that is urban dynamometer driving cycles, which is used to test the vehicles. Of course, I think this is USA based, USA. This is for the European country. And this is the developed our own driving cycle to test the vehicle operation. So once this driving cycles, we are providing these as the input. And this will provide the information about the driver nature, road conditions, and traffic conditions, along with the speed variation with respect to time. So let's say we have considered this vehicle, and the gross weight of vehicle is 610, curb weight is 272, means this is with the passenger, and tires and all other information which is needed that has been mentioned over here. And how much we are only considering the, you can say, longitudinal force which are acting on this vehicle. And basically there are 4 forces. One that is with the grade, other is with the tire, other that is aerodynamic tire, and the acceleration force. And this is can say the when it is running on the heel. So during heel operations, the inclination force. So we have this, you can say, the rolling resistance force, aerodynamic force. These are the 2 constant force which the vehicle is continuously demanding when it is running on road, whether it is in dynamic conditions or steady state conditions. This grade resistance force, that is whenever you are running your vehicle on a grade. And the acceleration force, that is always when you start your vehicle from 0 speed. And all of you know, you can have this CRM into G, half rho A CD into V square, and G sin theta, and mass into acceleration. And what are the power requirement of the vehicle can be calculated based on the essential data required for the computation of the vehicle power. So what is the required speed, efficiency of motor, rolling resistance, coefficient of drag, area of the vehicle, radius of the wheel, and mass factor. This mass factor is nothing but basically whatever the mass of your vehicle, plus the certain inertia will be offered by the rotating elements. They will also introduce additional mass, or they will also increase the mass of the vehicle. And that's why this mass factor will be usually considered as 1.11 to take care of that rotating parts mass contribution. The performance of vehicle is determined by the following factors: cruising speed, gradability, and acceleration. These are the 3 factors which we need to do. So let's say we have selected this as our driving cycle, and with that driving cycles and available vehicle data, we have calculated the power, and this is the power. Of course, this part, negative part, is nothing but whenever we are reducing speed, the power will be interpreted as a negative power, but it's basically not a negative power. Try to understand. There is always a positive power. If we interpret these as when the speed reduces, whatever power that has been demanded by vehicle, we interpret it, because it doesn't demand power, but it can supply that power. So that can be mapped as a negative power. Basically, it is not a negative power. And this is the energy during this whole trip, during the trip of, you can say, 500 seconds. This, how much energy that it consumes, including the effect of the regenerative braking also. So now how you can size your battery and supercapacitor. So from the this graph power plot, you can find that what is your maximum power, positive maximum power. You can determine the average power also, and based on that we got these 2 values, that is, this is peak power and this is average power. So if I am using UC, then UC has to supply this and the battery has to supply this. But let's say I'm designing only battery operated vehicle. So when it is a battery, then in that case the battery has to supply this much amount of peak power also, along with this average power. So the battery current, let's say I'm selecting the battery with the voltage of 48 volt without UC, assuming maximum current discharge per cell is 5 ampere with a peak voltage of 4.2 volt. Then how many number of battery cell we need to connect in parallel? That is 48 divided by 4.2. So this is 12 to be connected in series, and to get the, you can find the current also, because the discharge per cell is 5 ampere. The total current with respect to this peak power will be again this divided by 48 will give you 86 ampere. So this current has to be again supplied by battery. So you need to have the 17 number of this 12 series connected string will be now 17 strings should be connected in parallel to get this. So you can see that the size of your battery becomes very huge, even though it demands average power of 1.143 kilowatt instead of 4.123 kilowatt. And the battery current at 48 volt with UC, that means it has to supply only 1.143 kilowatt. So it is nearer to 23.18 ampere. And so 5 in parallel and 12 in series to maintain the same voltage level. And supercapacitor, supercapacitors will supply maximum current of 86 ampere. The Maxwell 300 Faraday, as I have told you, they can supply 100 ampere current. And the voltage is 2.7 volts. So 18 number of supercapacitor must be connected in series. No parallel connection is required to support this. So this way you can see that the size of your supercapacitor bank related with this high peak power will greatly reduce. And you can even determine the capacitance value, how many number of capacitors are connected in parallel can be calculated based on the resistance offered by your supercapacitor, which will be given by dV minus I average into dt by C. I average is nothing but because your system will have the V max and V minimum voltage. So when the voltage is minimum, same power supercapacitor has to deliver, so the current becomes maximum. And when the voltage is maximum, for the same power delivering, the current becomes minimum. So we are taking the average value of this. C is nothing but the total capacitors, which can be calculated as the capacitors of the individual cell multiplied by NC, number of capacitors connected in parallel divided by the number of capacitors connected in series. So this way, once you can find out this, you can have the value of R, or to have the integer value of R, positive value of R. You have to decide how many number of capacitors that can be connected in parallel. So that way you can find out the sizing of capacitor bank also. Of course, for that you need that for how much duration you would like to provide this power to the load. And this is the simulation that has been performed with this as a drive cycle acceleration, constant speed, deceleration, again acceleration, and constant speed. And in this case, if you can see that during acceleration, the torque will be positive. Constant speed, it requires less amount of torque. And when you are providing a regenerative braking, your torque becomes negative. And at the same time, if you will see here, your current becomes also negative. So this is the mandatory requirement to implement regenerative braking, that motor should supply current, not draw current, but it should supply current, and that's why the current should be negative. If current is negative, then definitely your torque becomes negative, and that will implement the regenerative braking. And this is nothing but the regenerative torque. As the time goes on, the regenerative torque reduces. Let's say here again we are increasing our speed, so torque value will increase in this value. The current becomes again positive. And this is the variation in the UC voltage reducing. Here it is almost, you can say, increasing from this, because during this two part it has to supply power, and during this part it gets charged and again it gets discharged. So this way you can have, these are the very simple and the few examples which I have shown you how to use supercapacitor for different applications with the power electronics device. There are different manufacturers, Europe, in USA, the Maxwell is the very well-known company now, NISCAP, and I think JSR Micro, NEC. These are the most well-known companies of different, can say, and the skeleton technology and the BedCap. These are the main manufacturing company for the, or well-known manufacturing company for the supercapacitor. Still, we do not have But still, I think in Pune, they do manufacturing of supercapacitor. So I hope that I have discussed almost related with the supercapacitor, about supercapacitor, their applications with a few examples. So thank you so much for listening me very kindly. Now, if you have any questions, you can ask me. Hello, I'm audible.
Madam, could you highlight some of the possible research avenues, especially for power electronics engineers, with respect to EV applications?
Huh? Yes.
Yeah,
You are not audible clearly. Power electronics. Hello.
Madam, able to hear me?
Yeah.
Madam, could you highlight some of the possible research avenues for power electronics engineers in EV applications?
Power electronics application in EV.
Yeah.
What
Actually, ma'am, he is asking.
Yeah,
madam, I'll repeat that question. He is asking that can you? Yeah, ma'am, I'll repeat that. Are you able to hear me? Yeah. So he's asking that can you highlight some possible areas of power electronics engineering in EV?
Okay. So now the first thing is that you cannot say EV. EV is nothing but an interdisciplinary area. And as far as the electrical branch is concerned, it cannot be realized without power electronics. Everywhere you need to use power electronics. To let's say the whole complete electrical vehicle, let's say I want to design a complete EV, then I am having basic two compartment. One is the source and second is a driver. Drive unit. So source is nothing but battery, supercapacitor, flywheel, fuel cell, right, etc. And drive unit will have the motor plus inverter. So those who are really interested in the motor applications, how to control the motor functionality, the why I'm telling you, say the motor which we are using in industry, their control is very specific, fixed way you have to control the functionality of that motor. Here the motor control is defined based on the driver nature, because it is continuously changing. Different types of driver will have different nature. So their speed demand will vary. Again, it depends on the road condition and the road traffic. So these things we have to consider. And that's why to control the motor or to design a control algorithm for motor, it is little bit tough compared to the motor which we are using in industry. And here the motor is again running on road. So you have to take so many other parameters also. So one of the area in which you can focus with the power electronics is a drive control. Select appropriate drive. You can have the drive means the motor, different motor. You can have the induction motor, BLDC motor, brushless DC motor. You can have the synchronous motor, PMSM. You can have the switch reluctance motor. Different motors configurations are there. Again, in either a hub motor or a separate motor which will be placed within the body of the vehicle. So you will have different options. You have to select an appropriate motor. Again, in these also you have the multi-phase concept, multi-phase motor, and that is very preferable for vehicle application, because if you want to have the continuous operation of vehicle and suppose you have a three-phase system, one of the phase won't work, then especially for induction motor and synchronous machine, you cannot drive your vehicle. So if it has a multi-phase concept, multi-phase motor, then you can have the continuity with the reduced capacity. Continuity of vehicle operation is there, but with the reduced capacity. So here you will have the selection of motor appropriately for your applications. Usually for the two-wheeler and three-wheeler, they are preferring BLDC motor, but still this BLDC motor, synchronous motor, they have the, you can say, the monopoly of the China maximum, because and the cost becomes is again a factor for the use of this permanent magnet type of machine, and that's why even at S focusing on application of induction motor in their vehicle. Even the Reva has already built his more, you can say the EV with induction motor. But now people are focusing not a three-phase motor, but the multi-phase motor. Other very can say preferred motor is a switch reluctance motor, but still it has some can say some restrictions in terms of I can say the torque ripple and noise. So you may take care of this torque ripple at the time of design of the motor, but to control this switch reluctance motor is much more simpler than the other motor, because the individual phase is controlled at a time. So the control of the switch reluctance motor is still easy compared to this, but having certain limitations, so that care has to be taken at the time of designing its control strategy or the control algorithm to control the functionality of EV motors. So you can focus on drivetrain, you can focus on the source design of hybrid power source or design of power source with the fuel cell and battery, fuel cell and supercapacitor, or fuel cell with the flywheel, or you may have the battery plus supercapacitor source. So there again you need to have the interfacing with the power electronics device. And this power electronics device interfacing may be DC to DC converter simple, or you can go with a complicated multi-phase configuration also. And similar way you can have the matrix converter for electric motor control. So that way you can focus on these two parts as far as the power electronics part is concerned.
Thank you, madam.
If you have any doubt, you can ask me.
Now, one more question we have here.
Yes.
What is the maximum range of ultracapacitors and how to test these?
Testing is usually very simple. I have not discussed that part. You can usually we do testing because, as I have told you, that the variation in the terminal voltage of supercapacitor is directly related with the variation in the stored energy of supercapacitor. So only measuring the voltage, terminal voltage of supercapacitor and the current drawn by supercapacitor, you can find out their SOC measurement. You can measure the SOC directly. It is usually the square of the voltage. And certain other tests are there. Usually we may go with the pulse power test. Supercapacitors are usually tested with the pulse power test. So we give a high current for a short period of time, and then we keep the supercapacitor rest for certain period of time. Then again, and as I have told you that it has some physical property, and this physical property will be interpreted in terms of the redistribution of charge when you charge it or when you discharge it. And that's why the terminal voltage variation will be there, and that's why you have to keep it for a certain period of time so that you can visualize that after a certain period of time, the complete charging of your supercapacitor has been done. And the maximum capacity that has been decided by how many number of capacitors you are connecting in series and parallel. Because the capacitor will be provided by its voltage rating, current, voltage, current, and the capacitance value. These three parameters are there, and based on that we can judge. And I have already shown you how to calculate the power density and energy density of the supercapacitor. I've shown you with the simple formula, the same formula what we are using for the normal calculation.
Ma'am, we have one question. That is, what are the major power quality issues we have to concentrate?
For?
What are the major power quality issues that we have to concentrate?
No, that is referred to EV you are asking?
Yeah, suppose, I don't know, wait, just a second. Yeah, I think he must be asking about EV itself. The question is asked by Dr. Tamiz Central.
Yeah, good afternoon, ma'am. Actually, even when you are using ultracapacitors, along with that, we are using induction. In induction motor, the inverter is used in that. So it has involved power electronic devices. So what are the major power quality issues in EV applications we have to concentrate?
So the first thing is, as it is not designed without inductor. So usually, if I say that for supercapacitor, the current ripple should be as minimum as possible, and the voltage, as I have told you that we need to have the DC voltage. Let me show you with this. This is your DC bus. This is your supercapacitor, and this is nothing but your converter. Right. So the first aim is that we have to maintain this DC bus voltage constant with respect to this, and while functioning this, the power quality issue is in terms of the ripple current. Ripple in a current supplied by this, because when we pass this power to the inverter, then definitely what we want that it get filtered out. So the voltage which we are applying to the inverter must have the minimum ripple, and the current supplied by this source through converter should have the minimum ripple. That is a basic requirement, and to have the proper operation of your motor especially. So in that particular case, you have to properly design this DC link capacitor also, even with the supercapacitor application. And it has a capability to operate with the high current. But as we have the power electronics device with us, it has a tendency, because we do the chopping, and because of that chopping, the ripple in terms of the power quality issues will be there, and you have to manage that. But you have to design your converter and the control algorithm in such a way that the current that has been drawn by this converter, that is the current through the inductor of this converter, must have the minimum ripple, as well as the voltage which we are getting at the DC bus must have the minimum ripple. Ripple should be minimum, and the constant magnitude of voltage is required. Otherwise, the inverter control becomes very difficult if we are not able to have the DC bus voltage constant. Then you have to implement a different strategy to operate your inverter with the variable voltage. That is the reason why we use this converter, so that it can balance out this thing. And other related issues, what you might be very much familiar with the motor functionality, isn't it? So we have to take care of that, and that care we are taking by simply generating a reference current from these motor, and based on that we are controlling the inverter functionality in such a way that again the current through the motor will have the minimum ripple. Ultimately, we are controlling the power for the source. So control of the source is in such a way that finally the current that has been drawn by the motor must have the minimum ripple. Or you can interpret in terms of the harmonics. So you have to adopt an appropriate control strategy for motor also, as well as for inverter. Hello?
Yeah. So I think, ma'am, hopefully the query is clear by the participants. So I think we don't have any more questions as of, ma'am. Participants, if you have any questions, you can ask now. Otherwise, we will stop the session here.
One more, sir.
Yes.
Can ultracapacitor work as a constant voltage source for some time?
It cannot. It cannot. Of course, if I'm assuming that for a certain period of time, for a small period of time, I can assume that variation in because this variation in voltage is not that much fast, isn't it? Because it is again related with your SOC. So you can, it's not, I can say, fast variable, means it cannot vary at very faster rate with respect to time. But of course, as time goes on, the terminal voltage of supercapacitor decreases when it is in a discharging mode. And maybe for a small period of time, that is a delta T, you can assume that the supercapacitor voltage is constant. So when you developed your small signal model, for that particular point only, you can assume that the variation in the supercapacitor voltage is constant, but not as a whole. And that is the reason why we prefer to have the converter. It is supplied with the converter.
Thank you, ma'am.
Okay, so I think the queries from all the participants are answered. I again thank you, ma'am, for your session, for the time you took out for a wonderful session on ultracapacitors and its use. Ultracapacitors is an emerging area, and most of the participants are not that much aware about this area.
Thank you.
And all the participants have made
I hope
regarding ultracapacitors.
the information which I have supplied to you or discussed with you may be very useful to you.
Yeah. So,
anything, you can approach me directly also. You can get my number from the coordinator of this course. And if you have any doubt or any query, you can ask me.
Yes, ma'am. Thank you. I'll share email and number as well with the participants once the FDP is over. And so participants can definitely get in contact with you regarding any of these sessions or maybe any of the fields for electric vehicles. So, ma'am, I thank you again for this wonderful session. And let us end this session here.
Okay.
So, participants, I'd like to tell you that our next session will start sharp at 12:45 a.m. Yeah, ma'am, you can leave, no problem. Thank you, ma'am. Participants, our next session will start exactly at 12.